So in the last lecture, we talked about Hilbert space. Again, looks very fancy, the name, but after all, it's just a linear space or vector space with inner product, and it is complete. Again, this complete, we did not discuss what it is. So whenever you think about Hilbert space, for the level that we are at, you can just think it as the Euclidean space. Anything worse in Euclidean space, 99.99% were in the Hilbert space. That can help you understand many things when you read paper or when people discuss the concept. We have 3 criteria for inner product. It needs to be positive length. So F inner product with itself must be positive. It obeys this F inner product with G, you get a scalar, and that is equal to the complex conjugate of G inner product of F. We also have this distribution rule, right? And then further, we say that if we try to write in bracket notation and also the column form, let's say A is a vector. How many dimensions is this vector, by the way? N dimension, right? Because I have n component from A0 to An-1. So how do I do the inner product? It is this. I'm going to show you today because we did not cover last time. And then we also will talk about measurement again. So I keep repeating. I hope that you get very familiar with that, right? So last time we talked about some basics of linear algebra. We talked about the vector space, linear vector space, inner product space, and then Hilbert space. So we look at two-dimensional space. Now, let's just recap again what is a bracket notation, right? So here I have 3 vectors. They are all equivalent if we agree upon something. This is V, a vector, equal to alpha times Vx hat and plus beta Vy hat, right? And here I would say these are the basis vector. Just like what you did in the Euclidean space, right? So this is the basis vector, which is Vx hat, Vy hat. Is this okay? I can also write it as the cat notation. Again, the basis vector here is Vx, Vy. It's just a notation. Okay? And similarly, if I'm talking about the cat notation, I can even say this. Assume this is a polarization of a photon. You even don't need to know what is polarization, right? You see, this is so abstract. Just the final polarization, the vector, right? You even don't need to know physically what it is. Final polarization of the vector is this much of horizontal polarization. What is the meaning of this much? Maybe alpha, if you want to give a number. And horizontal polarization, maybe I'm referring to Vx times that much of vertical polarization. So these notation are all equivalent. As long as you agree Vx hat equals to Vx in this cat or equal to horizontal polarization in this cat. You agree they are the same thing, they represent the same thing. Then these 3 vectors are the same. Any questions? Right, so think about this slide in the future. Whenever you see the cats, whenever you get confused, think about this. I can put an English sentence inside. They are representing the same thing. Okay? So let's go back to multi-dimensional space one more time, right? So if I have n dimension, this is actually very straightforward to many of you, probably to all of you. But we just want to write it out one more time. In n-dimensional space, I have the basis, just like the 3D space. It is a set of vectors. This is the basis, right? So I can write it as x0 hat, x1 hat, all the way to xn-1 hat. Is this okay? Just now I can say x hat, y hat, z hat. This is 3 dimension, right? Again, I'm repeating, right? I'm not introducing anything new. I'm just trying to get you familiar with all this symbol. I can write this as x0, x1 in the cat because these are just vectors. So I can write it like this. This is a set. I don't write it well. This is curly braces, right? A set of vectors, n dimension, right? Then we say in this space, if you give me any vector in this space, right? I can write it, let's say A, I can write it as A0, X0 plus A1, X1 plus all the way to AN minus 1, XN minus 1. Right? Looks like a lot of stuff, but again, you know that already. That's what you did in 3D space, right? 1x hat plus 2y hat plus 1z hat. That is what we're doing. We expand to n dimension. And particularly now I write it in the cat notation. So that is the first thing you need to think about if you got confused. Now, because I just told you that I actually don't care how I write that thing inside the cat, I can as well just say that this is your A0 plus A00, A11 plus A22 plus AN minus 1, N minus 1. As long as I already told you, this equals to this. Because this is just a symbol, I can even say ZERO, ONE, TWO, right? And N minus MIUS, ONE. They are the same, right? So get familiar with this. But it also means that you have to make sure that your reader understand what you're talking about. So sometimes when we read paper, what confuses me is which basis are they talking about, right? So you need to make it very clear if it is not straightforward. So now you look at this, you find that this is no difference from what you've learned from high school or middle school vector on the 2D vector. It's just the same. We expand to n dimension. Is this okay? And of course, that's interesting. Why I don't have dual space? Oh, I see. And I'm not discussing this on this slide. Okay, and then I can also write it as A0, A1, AN minus 1 as a column form. Okay, so maybe some of you feel very bored, right? Then let's move forward. Now you're very familiar with the cat. Cat is just vector, column form. Now, in linear algebra, we also have a concept called dual space. So what does it mean? It's just like the mirror image of the vector, okay? So I have a cat. For example, B. Its mirror image, of course, this is not the real mirror you see, right? But just imagine, we can find a relationship just like its mirror image, right? We usually would say they correspond to each other. This is called dual correspondence. Right? It has this relation to something called bra, B-R-A. And why it's called bra and why it's called cat, maybe you know, but if you don't know yet, later you will see why. Then we write it as B in the other side. Now you start seeing something, right? Hey, isn't this is the left-hand side of the inner product we have been talking about, right? This has nothing to do with inner product by itself, but it turned out that they have this relationship, right? We just write it as B pointing to the left. Okay, you accept it. You just agree with this. It's just like people tell you that, and all the matter has its antimatter. It's just like this, right? You accept it. Okay, proton has anti-proton, electron has anti-electron. Right? But electron is positive charge, anti-electron, which is positron, has positive charge. Now, we are not talking about that, right? I'm not talking about this equal to this, electron. I'm not talking about anti-particle equal to this, but just the concept. So now you accept it. I say any head in this linear space, I will have a corresponding bra. Okay, so this another dual space. So in this cat space, I have a bra space. They have some relationship. We'll see what they are, but just trust me, they have this relationship. So we just say that if I have a cat like this, I will write it as B0, B1, all the way to Bn minus 1 for an n-dimensional vector. Correct? Any question about this? How do we write? So here I say, okay, cat corresponding to bra. How about in matrix form? What is the form of bra B? It is just the transpose, B0, B1, all the way to Bn minus 1, and then add the complex conjugate to each of them. Take it as definition. Rotate it, complex conjugate. Done, right? So we call this conjugate transpose. And of course, the cat is also a conjugate transpose of the bra, because you transpose this one, you become a column, and then you take the complex conjugate again, then you star becomes nothing, right? So, okay. So let me ask you, if I have this vector, a general vector A equals to B0, x0 plus B1, x1 plus all the way to Bn minus 1, xn minus 1. What is its dual vector, or what is the bra version of A? In other words, what is this? You can guess, right? But based on what we talk about so far, what do you see so far? Right? You look at what happened for a cat when you go to bra. What happened to the coefficient when we go to bra? Is what? Complex conjugate for the coefficient, very good. Then how about for the basis vector? How do we write them? Bra version. Very good, right? So basically, I will just say B0 star x0, the bra version of x0, plus B1 star x1, plus all the way to Bn minus 1 star xn minus 1. That's it. Right? So any vector, for any vector in this n-dimensional space, is corresponding bra version is this, the dual correspondence. And turn out to be very easy. And all you need to do is just flip the arrow from right to left. All the number becomes its complex conjugate. And if you have matrix, just rotate them. Okay? So here is just a review of this space. We will talk about this a little bit later. But am I missing something? Yeah, so I'm wasting a lot of space here. Now, I want to ask you one thing. So let me just here. What is, this is not related to the upper one, right? So what is B? What is the best way to write this? Okay, sorry, for those who are taking note, right? I think the way I write it actually can confuse you later. So I decided to change this name. I do have this liberty because it's just a name. I want to call it B instead of A. It is okay, right? I'm not doing anything wrong. I did not violate any rule. I just recall it. I call it B. Okay, so similarly, I have A before, right? A equals to this, okay? So my question now is, combined with what we learned in the last page, what is B A? What is this? Or maybe let me write it in a better form. I write it B bra A cat. I can write it this way. But this is more convenient as just write it as BA. Okay, do you see this? I just have It means I have bra multiplied by cat. And now maybe you know why this is called bra. If I insert an alphabet here, it's called bracket, right? That's why the left one is called bra, the right one is called cat. Okay? That's the reason, right? But anyway, let's ask ourselves, how does it multiply? Now, we already say what is B in the matrix form. It's B0 star, B1 star, all the way to Bn minus 1 star. How about A? It's A0, A1, but it is column form. An minus 1. Correct. And you know how to do multiplication of a row and column, right? This is just matrix multiplication. This row times this column give you one number, one scalar number, which is B0 star A0 plus B1 star A1 plus all the way to Bn minus 1 star An minus 1. Right? We just reviewed last time. If these are orthogonal, this is nothing but just the inner product of the vector we said last time. Last time when we say if these bases are orthogonal, then, not here, the bases, we did not, this bases x0, x1, xn, if they're orthogonal, the inner product of two vectors is what? It's just equal to B0 times A0, but we did not talk about this star in Euclidean space because they are real, right? But here they are complex. So we did not say that this need to be inner product, but the formalism we wrote here, and then when we multiply the B by A, we get the inner product. So this goes back to our original symbol. We claim that this is the inner product. And now you understand why we claim this is the inner product, right? So I did not go through a sequential derivation to establish the whole theory. But now we just keep going backward, look at 3D Euclidean space, and then come to here, define this dual space, and you find that, yeah, turn out that they're just consistent. B, or the bra A cat, or B bra A cat, is just the inner product. So the symbol we have been using makes sense. And this turned out to be very useful later. So you need to get familiar with this. But at least at this stage, B, A bracket, right, bracket, is just the inner product. So you see that the dual space is the multiplication between the bra version of a vector and the cat version of another vector. That's the main point. When you do inner product, you take the bra version multiplied by the cat version. In our real 3D space, since it's all real, the number, so really doesn't matter if you take the complex conjugate. But now in the Hilbert space, it's different. It can be complex. Okay? Again, it would be great if you go to some of my book or other place to understand deeper. If not, fine. But now you really need to accept all this notation, okay, and remember the rules. Good. Another thing I will say is about the superposition and the measurement, right? So we talked about this already in the introduction. Now we repeat again, but we have a little bit more math. So again, any vector A, we are repeating what we said, equal to A0 times x0 plus A1 times x1 all the way to An minus 1 xn minus 1. Right? This is a general vector. But let's just look at a simple one, 1 qubit. Then for example, So the good thing about quantum computing, at least the introduction part, is actually very easy. You only have two-dimensional space. For example, you have 1 qubit, right? For any 1 qubit, you are going to have psi equals to alpha 0 plus beta 1. Again, I hope you can relate this. Here, A0 equals to alpha. X0 equals to 0. A1 equals to beta. X1 equals to 1. I have all the freedom to write 0, 1, up or down, English or Hindi, whatever. Completely okay for me, right? So do not feel confused why this is X0 now becomes 0. It's just a name. But once you start working on the problem, you need to fix what the meaning it is, okay? So this is 1 qubit. And the question is, okay, actually I want to write more as what just said. This can be alpha up plus beta down. I can also write it in column form. What would that be if it is in a column form? Alpha, beta. Thank you. Right? So the only thing I want to say here is, if you do a measurement on this state, right, it will collapse. The wave function will collapse randomly. Okay? Randomly collapse to can be 0 with a probability equals to alpha alpha star, which is equal to alpha magnitude square. So this is another equation I want you to memorize. You already know, but just review. The magnitude square of a complex number is itself times its complex conjugate. Okay? Or it can collapse to 1 with the probability equals to beta beta star, which is equal to beta square. Is this okay? Any questions? Yeah, that's what I want to say for this, that actually from last lecture. Okay. So I know it's very simple. We keep repeating, but make sure that you understand this basic. Okay. Now, then we go back again. I keep talk about orthonormal basis and normalized vector. I did not talk about normalized vector, but we mentioned this many times. So what are they? We have been assuming we are using orthonormal basis, but now it's time to make this clear. And throughout the whole class, we will use orthonormal basis most of the time. And if it is not, then we need to mention. Sometimes you thought that you find something very strange, something unexpected. It is mostly because you did not use orthonormal basis, right? You try to apply a theorem to a orthonormal basis, then you will get something very weird. So watch out for this, okay? Now, if you are given basis, let's say for a basis, right? Again, what is the basis? Just like in the 3D space, you have x hat, y hat, z hat. In the n-dimensional space, I have x0, x1, all the way to x. What is this? Let me write it slowly. xn minus 1. N-dimensional spaces, right? So this one is orthonormal, right? We call it orthonormal if xi, xj. Can someone tell me what I just wrote? What is the meaning of this? What I just wrote? Xi, xj bracket. What does it mean again? The inner product of what? The two bases, xi and xj. So meaning that I just randomly pick allowed to make any two bases from there. For example, x, y, z in three-dimensional space, x hat, y hat, z hat, right? I can pick x hat inner product with y hat, x hat inner product with z hat. So depends on what I pick. So I and j just signify that it can be any of this. So I pick any of this and do the inner product. What should the result should be if it is orthogonal? So he say it needs to be 0. Is this all the case? This is only the case if I not equal to j. Good. Not equal to j, right? X hat inner product with y hat, they are perpendicular to each other. So their inner product is 0, right? X and y. Y and z. C and x. Because I not equal to j. So they are 0. But what if they are the same, right? Because although I write it as j, but I'm allowed to have I equal to j, right? After all. So it means x hat, y hat inner product y hat, or z hat inner product z hat. Right? But we generalize it to higher dimension. So what would that be? Based on your experience, right? But this is definition. 0 means orthogonal. 1 means normalized. So basically it's saying that your unit vector all have a length of 1 and they are perpendicular to each other. But in the n-dimensional space, we don't know what is the meaning of perpendicular. Right? We cannot visualize it. It is defined by their inner product being 0. Okay, so this one you will see many times, although I should not waste so much time, but it's good to make sure. So this is orthonormal basis, okay? Now, then, good, this is orthonormal. Then, this is just the basis, but how about for generalized vector? In quantum computing, the generalized vector need to be normalized also, not just the basis vector. So let's take a look, right? Consider vector V. This V can be written as A0, this X0 plus A1, X1, all the way to AN minus 1, XN minus 1. So again, I have N bases, right? Because it's orthonormal basis, right? If this is an orthonormal basis, if it is an orthonormal basis, you will find that V equals to, as we mentioned many times, equals to A0 star, A1 star, AN minus 1 star, times A0, A1, AN minus 1. Again, I'm just repeating we just learned. The inner product of the vector itself is the bra version times the cat version. And the bra is row complex conjugate, and the cat is just column itself, right? What is this again? Equals to A0 star, A0 plus A1 star, A1 plus all the way to AN minus 1 star, AN minus 1. Is this okay? We did that already for B and A. Now you just do B, A and A, right? And we just mentioned the complex conjugate of a complex numbers, complex conjugate times itself is just the magnitude square. So this is just equal to this. All right. But remember, we talked about the measurement. What is the meaning of this square of the amplitude? It basically is saying that this is just the probability of getting x0 plus the probability of getting x1 plus all the way to the probability of getting xn minus 1. Right? So the length square of a vector is the sum of the probability of getting the basis state upon measurement. Any question about this? This is important to clarify. Any questions? Feel free to ask. And maybe I can go back to here just to mention, make it clear when you study, right? So this is nothing but just equals to the probability of getting 0. This equals to the probability of getting 1 when you measure the state. The probability of getting 0 and 1 equals to the square of the magnitude of the corresponding coefficient. So same here, although it's n-dimensional space, I find that the inner product, which is the length square of this vector, equals the probability of getting each of the basis state upon measurement, right? Because this one is the sum of this basis state, right? Physically, what should this sum be? Should be 1, right? Because I must get something when I measure. I cannot add together to be larger than 1 or smaller than 1. Right? It's just like drawing. I have n possible output. The total probability of getting each of them must be 1. I must get one of them each time I draw. Right? So in that case, what should be the length of the vector square? I mean, the square of the length of the vector, if it's want to be physical meaningful. It must be 1, right? So all quantum states must have V equals to 1, which means normalize. Right? You need to be normalized. So when you're doing your computation, you find that your length is larger than 1, you know you have made something wrong. If you come up with a new quantum computer, somehow your length is shorter or larger than 1, you have done something wrong also. That is not the right one, right? You need to check it. So this is a way to check if you are doing something right. So at this stage, right, even you forgot the method, the most important thing is we work on orthonormal basis. It means all the bases, x hat, y hat, z hat, or whatever hat and dimension should have unit length. Second, they need to be perpendicular to each other, orthogonal to each other, means the inner product needs to be 0. And for quantum computing or quantum mechanics, the state of anything, any state, need to be normalized, means that their length need to be 1. Okay, so, and then in that case, the basis is just a special case of this. This is a general vector. Okay, this one you need to memorize it, don't lose it. So with that, we have a pretty good idea. Now, I want to just briefly touch upon the concept of changing bases. Last time we already learned how to represent one vector on 2 different bases, right? So here I want to mention to you, I call this 0, this 1 is just a name. If it is in a 2D space, you call this x hat and y hat. This one has nothing to do with quantum computing, not the Hilbert state we're talking about. This is just something for visualization. I need to emphasize this. This actually confused some people. And similarly, I also introduced another coordinate. I call this minus, this plus. It's basically just a rotation of this coordinate. And then I have this, I can also represent this vector in this, right? So I could have just put x hat, y hat, and then put a corresponding 3D space vector for this basis, And in not using psi, just use V arrow, like what we did in high school algebra. But I put this just to show that they are equivalent. The name doesn't matter. And more importantly, I want you to get used to this cat notation. But the concept is the same, right? So let's start with this. Now, I can have two bases. Now I call this 0/1. It means I'm working on this basis. Still the same 2D plane, but I want to express in this basis. Just like the egg analogy, I just want to say how many eggs I have bought instead of how many dozen I have bought, right? So similarly, I have another basis. On the same 2D plane, I call it plus, minus. Okay? Now, you give me a vector. You say, okay, I have a vector xi equals to alpha 0 plus beta 1. Of course, and now I came that alpha square plus beta square equals to 1. Are you okay with this? Why I can say that alpha square plus beta square needs to be 1? Because I'm working on normalized vector. Thank you. So this is one condition you're going to use in many derivations. It reduces the degree of freedom. Okay? So of this one, and I say, okay, I also can write psi equals to alpha beta. This is easy. We already did that many, many times. Okay? But now I want to represent in the plus minus basis. I don't want to say 18x. I want to say 1.5 dozen x, right? Just like here, I want to say psi in terms of plus and minus. So how do I do that? First of all, I want to give you, given the 0 is actually 1 over square root plus minus. And 1 is 1 over square root plus minus. This is given, but you can derive just looking at this 2D plane, right? Because 0 is here, right? 1 unit of 0 equal to 1 over square root of plus 1 over square root of minus, because they're all vector. These two vector pointing in this direction will give me this direction, right? You all know this vector addition well, right? They will give me this. So this is like 0, this is minus, this is plus. And as a result, 0, you go through the trigonometry, you get this 0, right? Nothing surprising. Any questions? And I call it given, just say that I don't need you to derive it in this slide, right? You just trust me. So then, what is psi? Well, psi equal to alpha 0 plus beta 1. I can do substitution because 0 is just 1 over square root plus minus. And then this one plus beta 1 over square root. Keep writing. Plus minus. Is this okay? I just substitute 0. This is a vector, remember, no matrix, right? Do not feel confusing. I'm talking about vector. This vector equal to the sum of this vector divided by square root 2. I just put it in. This equal to the difference of these two vectors divided by square root, I put it in. Right? And the rest is just algebra. It's just equal to what? I group the term for plus. It becomes 1 over square root alpha plus beta plus. The other is 1 over square root alpha minus beta minus. Right? I have the freedom to do that, right? I mean, no freedom, I just follow the rule. Right? Correct? I want to write it in a column form. Then it becomes this. Am I right? Let me check. Yeah. So again, This equal to this. They are the same vector. But again, I asked you last time already. They are the same vector, but does it mean that alpha equal to alpha plus beta, beta equal to alpha minus beta? These two supposed to be the same physically. They all relate to this one, right? Can you tell me again why they are the same, but looks like the coefficients are different? Because the inter-order basis. Because this means alpha part of what? I have alpha part of 0, beta part of 1. This one I have alpha plus beta part of 0 or 1. None of them, right? Plus. I have alpha minus beta part of minus. And remember, not just alpha plus beta, but over square root 2, 1 over square root 2, times 1 over square root 2. So you usually don't change bases in this way, because you change it this way because you can see it. But we're talking about hyperdimension. So later I will tell you how to use the matrix, transformation matrix. But this is just a feeling, right? So everything can relate to what you see in real 3D, the concept. Okay. Now, then what I'm doing here is a little bit confusing later. So I think I confused quite some people by using this 2D fake example to relate 0, 1, and plus minus bases. The equation turned out to, later when you do the qubit, you also have 0, 1 basis and plus minus basis. The equation turned out to be correct, but this is a fake example, right? This is not the real plus minus and 0, 1 relationship, so please do not get confused. This is just a fake representation, but this equation are correct. 0 equal to plus minus divided by square root 2, 1 equal to plus minus minus divided by square root 2. Okay? Just come back to read it if you feel confused later. Okay? Any questions so far for the changing basis? Now, if no, then